Right. Better put a microphone on, and we have the chance of recording it. Okay, so we're coming towards the end. We're not quite there yet, but we'll get there. And we hopefully have some time for some revision as well, which will be helpful, I'm sure, for you. So we've got a little bit more to go on stuff to do with frequency. So we're going to be looking at frequency-dependent amplifiers today, and what that leads to. And it links in quite nicely with Paul's control stuff. I'll try and link the two together, and maybe a few light bulbs will go on. Maybe a few go off, we don't know. But there's some momentous news today. It's Shuran Lee's birthday. And he has asked the class to help him celebrate it with a round of applause. Although, to be honest, celebrating getting a year older, you get to my age, you don't do it anymore. Don't wish your life away. Avoid birthdays. Have it on a leap day. Anyway, well done for making it this far. Right, frequency-dependent amplifiers then. So, thus far, we have examined linear amplifier configurations that are frequency invariant, which means they don't change their response, whatever frequency you put into them. Amplifiers. They'll amplify 1 kilohertz, they'll amplify 10 kilohertz, they'll amplify 100 kilohertz. All right? There it go forever. Okay, there's an obvious flaw with that argument, but there you go. So now we're going to expand these circuits to linear frequency-dependent circuits, which change their response with frequency, depending on what frequency goes into them. And this, you may have heard of them as filters. Filters are very useful and powerful devices, and it's good to be in control with them, but it gives us an extra dimension to play with, which can be tricky to sort out. So we will start with integrators and differentiators, because we're op-amps and we like to do operations. We've done the adding and the subtracting, we've done the multiplying now and the dividing. So let's do some harder stuff. Let's do A-level maths. Do integrators and differentiators. But before we do that, we have to sort of make this conceptual leap. So you'll have done stuff with Paul in terms of control, and you will have done something called the P operator. Does that ring any bells? Yeah? And really, the P operator, you can really replace it with J omega. Is that ringing any bells? Yeah. P, J omega. P is an operator. But P, sadly for you, is just an abbreviation, believe it or not, of S. We have a lot of transforms involving letters. And as you go through your university career, you will come across more and more of these transforms, all the way up to the Z transform. So we've got a way to go. We fill in the gaps on the way. So we've done P. P is this J omega P operator, heaviside operator. But it's only part of something called S, the Laplace operator. Have you come across Laplace? A bit unsure. Not sure about that. Okay, so the Laplace operator is a sort of a transform that allows us to basically do differential equations easily. Makes it all adding and easy. But we're not going to worry too much about that. We're going to apply this kind of idea to frequency analysis. So for electronic systems in general, we're going to be interested in two things. How they respond to different frequencies that are not actually changing. You know, there's obviously, the signal is always changing because it's AC. But let's say there's a 1 kilohertz fixed tone going into your amplifier. You want to know how the amplifier is going to respond to that fixed tone. And hopefully, just going to make it bigger. Okay? So that's how it responds to different frequencies that are not changing. You're also going to want to know how they respond in time to different inputs, e.g. the step response. If you kick your amplifier with a step, suddenly turn it on, the output is going to go from nothing to some output, and it's going to get there in some kind of time response, and it could either wobble like mad or it could get there slowly or whatever. And we're going to be interested in how that operates. What tends to happen is that response dies away with time and leaves you with the steady state response of your 1 kilohertz tone that's being amplified. So if you kick something, it responds, and hopefully that response dies away over time to 0. So if we just accept that we're going to be looking at the response that's died away to 0, that the response that's left after the transient, the dying away to 0 response has gone away, that leaves us with j omega, or p, if you like. If we're interested in what happens all the way through until that condition occurs, we need something else, and that is this part of the complex number, sigma. Okay, so S is equal to sigma plus j omega. So it's an extension of P with this extra real term in this complex number that allows us to define what happens over a finite period of time when we kick the system with a step response and find out what happens to it. So this is usually sort of described, and it used to be in the good old days when people had cars, that it would be the suspension. If you bounce the car suspension, it wobbles up and down. And that's the transient response. And eventually, hopefully, that goes away, and you're left with the car just sitting there not moving. And that's the steady state response. Okay, and as your shock absorber wears out, when you bounce the car, it carries on bouncing. Yeah? And that's when this response here becomes significant. So in passive systems, it will always die away. It will always decay to nothing. In active systems, it's possible, and imagine can you imagine a car suspension where you bounce it and it bounces and it gets worse until the car is jumping down the road? Yeah, some of these pumped up things. That's what you can get in active electronic systems effectively. You can kick your amplifier and it will wobble, and sometimes they will wobble and go forever, and that's called an oscillator. Okay, and this is all defined by what's going on in this kind of expression here, which is the solution to differential equations. This is the exponential bit of the e to the whatever solution in the differential equation solved. Okay, so that's what we're looking at. So if we want to look at a whole system, we've got to look at this S parameter, which encompasses a steady state response in one dimension, or one direction, and the transient response in the other direction. And this allows us to draw all kinds of clever pictures that allow us to get an easy snapshot of what our system is likely to do. Yeah? So all this is trying to help us get to a point where we can understand the response of the system by looking at its transfer function in some detail. So you've done this with Paul. You've looked at second order systems in some detail, I imagine. And you'll understand that they can bounce and wobble and they can rise up and all this kind of stuff. And this is a way of describing them in graphical form that relates particularly to electronic circuits and helps us understand what's going on in the circuit. Okay. So, mostly, we are interested in the steady state response of the system. We accept that it's going to be stable because we're competent designers. We're not too worried about that at the moment. So we want to know what's the overall response of our system. So if we can replace S with just j omega, so we set the sigma to be 0 in this case, we're just effectively using Paul's P operator, we get the frequency response of our system. Okay? And that's what we're going to be interested in. But we have to remember that there is this other factor that is transient, normally, which affects how we get to that response. Right. So, we try and plot this with something called a Bode plot. That's one way of doing it. And a Bode plot has two parts, amplitude plot and a phase plot, because we're trying to plot a complex number against itself, really. And what we end up with is a frequency scale increasing. So this is telling us what's happening with frequency. And we've got low frequencies at this end, and we've got high frequencies at this end. And we've got amplitude on the y-axis. So this is the magnitude. So if this was an amplifier, with no frequency dependency or whatever, the frequency against gain will be a straight line at whatever gain you've got, say 10. It'll go all the way forever. And that will be your frequency response. Okay? But that's ignored the phase response. The phase difference between the input sine wave going in and the output sine wave coming out. There will be a difference in phase between it, because it takes some time to get through the system. It's going to be delay. So delay is a phase shift. So we should also really plot the phase difference as well. So on the right-hand axis, we've got a phase angle. And see, in this one, the phase is dropping down from minus 90 to minus 270 degrees. That's the dotted line. Okay? And the phase becomes really important, because if you feed back a signal, a lot of these systems are feedback signals. If you feed back a signal that's got a phase difference compared to the input of 180 degrees, and it's a negative feedback system, you've actually turned it into a positive feedback system, because there's too much of a delay. The output can't respond quick enough to the input, and it just gets worse and worse and worse and worse. So the phase response at certain frequencies becomes really, really important when we start looking at stability of negative feedback systems in particular. Right, but for normal systems and the level we're looking at, we tend to ignore phase. We say we're quite happy, the thing's stable, we're going to ignore the phase, and we're just going to look at the amplitude response against frequency, and that'll give us our steady state frequency response. Okay? But we just have to remember, there is also a phase response as well. So if your circuits start doing funny things at certain frequencies, remember something funny going on with the phase delay across the system. So the Bode plot is really just plotting that the complex number in terms of amplitude and phase. So we can describe the complex number in terms of amplitude and phase. That's what this is doing. But the amplitude is the thing we're interested in. So if we get good, we can look at the complete Bode plot with the amplitude and the phase, and that allows us to get some idea about stability. But we won't worry about that just yet, but just have to bear that in mind. Now, unfortunately, I've got to go through this because it starts to become important. You'll do it a lot more in the second year, I think. Okay, so it's very common for people only to look at the amplitude plot for frequency response. So remember, that's got modulus lines next to it. It's an amplitude, taking away the minus signs. And you've taken the amplitude of a complex number as well. So that's what we're going to do. But just remember, there is a phase response, because you're only plotting half of this complex number. So, most times it's okay, but just remember there's something else going on. Okay, so the amplitude plot shows us how the amplifier responds eventually to different frequencies when it's all settled down. And this allows us to relatively simply make good estimates at how a circuit may behave at different frequencies, which is what we're looking for. Come up with a circuit, we want to know what's its response, its amplitude response with frequency, and this will allow us to get somewhere there. Another way of looking at this S complex number is with a pole zero diagram. Have you come across pole zero diagrams? No? Okay. Yes, you have. You sure?
I believe so. We did the pole zero diagrams in control, yes.
Good. Okay. All right. So pole zero diagrams are another way of looking at that complex number. What we're plotting is the real part and the imaginary parts on a Cartesian plane. So instead of Bode plot separating it and looking at phase and things, a pole zero diagram is just looking at the whole S plane, if you like. So they're a really common way of looking at systems, and they're quite useful. They plot the roots of the transfer function on an Argand diagram, complex number diagram. Okay? And they're a very useful way of getting indication of stability. As a rule, general rule, poles, certainly, should be located in the left-hand plane for guaranteed stability. So if you can plot on an Argand diagram where the poles of your system are, you can just look at it and go, that's stable or not stable. Rule number one. Really useful thing. Okay. So what are our poles and zeros? Zeros are the roots of the numerator of our transfer function. So here's a sort of a transfer function. It's some fraction-y thing like that. The zeros occur for the roots of the top bit. In this case, there isn't any. And poles are the roots of the denominator of the transfer function. So when does this bottom bit equal 0? That's the pole. Gives us an infinite response. That's why it's called a pole. Solve that equation to give you an infinite response, where this fraction here is 0, when that lot equals 0, that's where your pole is on the diagram. So, right. So, a pole appearing at the origin, for example, in this case, when omega, the only thing we can play with is omega in this diagram. Okay? Frequency, we replaced S with j omega, and then we're just going to take the magnitude, just take the omega part. Omega gives us a response, or the denominator response of 0 when omega equals 0. That's the only point that can happen. So we've got a pole at j omega CR equals 0. Therefore, happens at omega, this W is omega, okay, equals 0. The gain is therefore infinite at omega equals 0. And omega equals 0 is DC. Okay? And this is very easy to spot from a pole 0 diagram. And a gain of infinity at a 0 response is an interesting case that does happen, or tries to happen, in a lot of cases. And it's not normally a good thing. Right. So let's just bear that in mind. And let's consider our general inverting amplifier circuit. So we know that the response of this, in terms of its transfer function relating V out to V in, is Z2 over Z1. With a minus sign, we're going to be strict about it. And that's what we've got. And we've considered resistors in here, and we've considered nonlinear things like diodes. But what we're going to do now is consider what happens when we put a capacitor in the feedback loop. Okay? So this is a frequency-dependent system. Because we can look at this and apply what we know about capacitors and frequency and get a good idea of what's likely to happen. Because at DC, so just go to extremes, at DC, a capacitor is 2 plates and is an open circuit. Nothing gets through. It's an open circuit. There's no way through. So we have no feedback from output to input with a capacitor there at DC because the circuit is broken. Okay? So this is effectively now a nonlinear system because whatever happens here cannot affect the input. Therefore, it has no control over keeping this virtual ground in place. Open loop now. And, you know, that's not what we probably want. Maybe we do, I don't know. At high frequencies, capacitors have very low impedance at high frequency. They become short circuits at high frequency. So now we've got loads of feedback, stabilizing it. So we maybe expect the gain to be very, very low at high frequencies because we've got this giant amount of feedback maintaining the difference here at 0. And if the difference there is 0, the output will be 0 as well. So you can get an idea of what's going on here. And we can see it's frequency dependent because at DC it's got one response and at AC at infinity it's got a completely different response. And the real question is, what happens in between? This is an integrator. So in general, we can analyze this with our standard techniques. And the current in the capacitor is defined by the function of a capacitor, which is C dV by dt. And that comes from Q equals CV, and dQ by dt equals I, and so on. So that's a trivial thing. We should all know that. But more specifically then, IC, capacitor current, is equal to the difference in voltage between the input and output by dt. So we've got 0 at one end, because we're assuming a virtual ground, and then we've got minus V out at this end, because if this is 0 and we've got the current coming in this way, this has to be a negative current. Standard way of approaching a virtual ground analysis of an op-amp. And obviously I in, which equals IC, because that's the rule, it's got to go around the outside, because it's infinite input impedance here, is equal to V in over R, because this is at 0, this is at V in, and the value of R is known. And those two currents must be the same, so we can start to say that this is equal to this. Right, thus V in over R equals minus C dV out by dt, equating them virtual ground. Therefore, you can rearrange that a bit. dV out by dt equals V in over CR, or V out is 1 over CR integral V in dt. Okay, because we've integrated the differential to get our value of V out, because that's what we're interested in. Turns out to be related to the integral of the input. So V out is proportional to the integral of V in, with a scaling factor of 1 over CR in front of it. Standard virtual ground analysis, straightforward. That's our transfer function, because it relates V out to V in. All right, so that's what we've got, an integrator. There may be some minus signs missing. Yeah, there's a minus sign missing here, sorry. So this is true, there's a minus sign on this one. Straightforward analysis, turn the handle, that's what comes out. Excuse me. So we can also think of these in Laplace terms, or impedance terms, if you like. We go back to our beginning, and we can say V out over V in equals minus Z2 over Z1. Okay, another way of describing the impedance of the capacitor is, the impedance of the capacitor is 1 over J omega C, J omega C, or in the steady state form we can replace the J omega with S or P, whichever you want to do. So it becomes 1 over SC over R1, and that leads us straight away to this transfer function minus 1 over SCR1, where S implicitly implies some kind of frequency response. And we can choose to replace S with J omega if we want. We can replace it with P, or we can replace it with the full S, the sigma plus J omega, if we're interested in what happens when we turn the thing on in the first place. So you could have gone straight to this, just using the J omegas. You could say the impedance of a capacitor is 1 over J omega C. This, I'm hoping, is well known. And rearrange that, and you get 1 over J omega C. And if we replace J omega C with S, or J omega with S or P or whatever, these are the same. All right. These letters are just abbreviations to remind you that there's something to do with frequency going on in that space. Right. So there's a bit more warning here about, remember, S equals sigma to J omega. So there are issues. Right, so this is what we plot on a Bode plot. We take the magnitude of our transfer function, which gets rid of the J's, and we plot that. We change frequency and we do a plot. So we say frequency equals 0, 1, 2, 3, 10, whatever. Plot it, and that gives us our frequency response. So there are several interesting points to note about this function. If we increase omega, we reduce the magnitude of the transfer function, because omega is on the bottom of the fraction. Yeah, so make omega bigger, magnitude of fraction gets smaller. As omega tends towards infinity, the value of the transfer function tends towards 0. At DC, omega equals 0. So the transfer function is infinite, which we sort of suspected because there was pole business going on. RC, the time constant, influences the rate at which the transfer function changes with frequency. It's a sort of scale factor going from infinity to 0. Big range. Okay, but we've got control over CR. We can change the value of C and we can change the value of R. So we can manipulate that response a little bit. So let's simulate this circuit. And let's make it easy for ourselves. We use a value of RC equals 1. So we just pick a value of R and a value of C that multiply together to give us 1. Okay. Say, for example, R equals 1 mega ohm and C equals 1 microfarad. Okay, so it gets rid of the CR. We expect the gain at DC to be very high and the gain to be lower at higher frequencies. That's what we've established by looking at it. Given that CR equals 1, when omega equals 1, we would expect the magnitude to be 1. Okay, and that's a magnitude of 1 is a useful feature to understand. Okay, so in hertz, this will be 1 over 2 pi, or 0.16 hertz. Okay, that's when the magnitude of that response is 1, with our time constant of 1. So if we can simulate that, plot it whatever, you can see that we get, as you'd expect, sort of an exponential decaying response, which if we went further than 1 hertz, would decay away to 0, or close to. And if I hadn't truncated this axis here, at 0, this would have gone up to infinity. Yeah, or as close as it can get. And at 0.16 hertz, gain is 1, or the response is 1. Okay, so this straightforward plot of that response, it shows the problems of plotting with linear scales. This is plotted in linear. We're going up in regular steps on both axes. And if I'd gone a lot further here in this scale, this bit would have been squashed right down. If this instead of being 4 volts, that had been 100,000 volts or something, we'd have had a response that came right down and was really flat along here. You'd have lost all the detail at anything higher than about 0.01 of a hertz. Okay? So we can do something about that. We can plot the axis in a logarithmic scale, because a log compresses things into powers of 10. So if we plot both axes, take the log of both axes and then plot it, that exponential function turns into a straight line, which is easy to draw, easier than exponential. So all we've done is sort of compressed, expanded the axes in a logarithmic method. It's a sort of a mapping, if you like, and it's reduced that into a straight line response. So this allows us to represent the transfer characteristic of this single pole response as a straight line, with 0 dBs representing a gain of 1 in the linear world, because that's the nature of logarithms. Notice that the frequency axis can never get to DC. You can't have a log of 0. And that's the way of avoiding this infinite response on this graph. We're going in powers of 10 here, so we could go further to 1 millihertz down here, and the line would just carry on going up as a straight line in terms of dBs. But the dB is hiding a lot of stuff. But it's a way of being able to draw these giant scales in a sensible way and get something useful out of it. But you can see where 0.16 hertz has now moved to on our scale. Yeah? There it was down here, and we got this. So what we've done is just stretch these axes out in a non-linear fashion to make that into a straight line. And it's pulled this point further over here on this scale. All right. Right, so now we are in a position to look at the integrator's performance. We see from our chart, which is representing frequency against amplitude, that it is fundamentally frequency dependent. Okay? It accentuates low frequencies, gets rid of high frequencies. It doesn't have a straightforward gain anymore. Thus we can call this a low pass filter. Okay, it's passing low frequencies, stopping high frequencies. Okay, but its performance near DC is a bit less practical than that, because in theory it has an infinite gain. All right. So what does that mean? It's fundamentally an integrator. We need to think about what happens when a DC level is integrated. So if we apply a DC signal, say 1 volt, to the input of this system with the resistor and the capacitor in it, which you can think of being a step, it's gone from 0 to 1. Okay, so you've got this non-zero input going into it. If you integrate that, a constant, you integrate that against time, you'll end up with a rising line. Integral of A is our DC level, dt, is equal to AT, which is increasing with time, plus constant, which constant we'll ignore. So it describes a rising value as t increases. So this means that if we apply DC voltage to the input of an integrator, then the output will rise linearly. Yeah? In principle, forever. There's no, as time goes on, this number just gets bigger and bigger and bigger in the abstracted world anyway. In practice, it'll only ever rise to the supply value because the amplifier can't amplify outside of its supply value. So it'll go to the supply rail, one or the other, depends which way, and just sit there looking at you. Okay? So it's like a drift. It's drifting from the value you want it to be up to an infinite value or the supply rail, whichever is smaller. And that's the nature of the DC response. It just goes forever. Doesn't mean that it's an instantaneous response to infinity. It just means it's going to drift slowly over time, potentially. And the rate at which it drifts is controlled effectively by RC. Right. So we've learned quite a lot from this circuit just by sort of applying a bit of common sense, looking at a frequency diagram and trying to relate what's going on. So we can put the Bode plot together for this integrator. We know it's going to be a straight line. Further, we know, or we will know, that the slope of that line is 20 dBs per decade. So increase the frequency by a factor of 10, the amplitude changes by 20 dBs for all first-order systems. Yeah? First-order systems will always have a slope of 20 dBs per decade, so it's even easier to draw on log paper, or just sketch, if you like. And the only interesting point is, where do we position this line? We know its slope. Where do we position it on this axis? So we need a point. And the point turns out to be, or the easiest one to work out, is where does it cross this axis here? Now remember, this is a 0 dB axis, which equates in linear terms to a value of 1. All right? So we say, what's the value of the transfer function, or what's the value of omega when the transfer function is 1? And that gives us the crossing point for this axis. So if you've got the crossing point and the slope, you can draw the line. And the slope is always 20 dBs per decade. Draw it. It's easy. Yeah, you just got to do a bit of basic algebra to solve V out over V in, which is the transfer function, equals 1, and work out what omega actually is. And omega turns out to be 1 over CR1, 1 over the time constant. So you haven't even got to do the sums. You've just got to look at it, know that 1 over omega 1 is CR1, or omega 1 is 1 over CR from time constant. Mark it on here. So you don't even have to do the sums. You've got to do them once to figure out what's going on. And then you go, oh yeah, it's obvious. I can draw this. This is easy. All right. So that's what we've got. That fully defines that system in terms of its amplitude response only. Transient response, we've ignored. All right. So considering what we know about op-amps, this type of circuit will not work effectively as a filter because of offset voltages in the op-amp. There will always be a small DC input into your op-amp because we can never get 0 in and 0 out from an op-amp. There's always going to be an offset, which means it's always going to drift. All right? Okay, so that whatever you do, best op-amp in the world, it's still going to drift eventually. It could take a long time. It could take months sometimes. And that's fooled a lot of people. They think their circuit is fine, it works for several months and then stops working. And this is because they've forgotten about this drift. Very slow, but it gets there in the end. So just remember, this will catch you out. And we can infer this type of behavior from the Laplace transform. So we just go back to our transfer function in S, j omega or p, whatever you want. And you can look at that and you can go, oh yeah, there's a pole at 0 there. I can look at that denominator and go, at omega equals 0, that solves to be 1 or 0. And that gives us a pole at 0. And we know now that that means that this is unlikely to work in practice. Yeah? Just by looking at the transfer function now, and a bit of diagrams and all that kind of stuff to help you. We can plot that on a pole 0 diagram. We've looked at a Bode plot. But a pole 0 diagram becomes very boring for such systems. All right? So we plot sigma and j omega, the S. We break the S into 2 bits and we plot what's going on from solving that transfer function. It's a trivial one because we know the pole is at 0. And so we just put a cross to mark a pole at 0. All right? And if you know anything about systems, you will know that a pole on this axis means that the system is marginally stable, which means if you don't do anything to it, it's likely to behave itself, but as soon as you do something to it, it becomes unstable, which is the nature of the infinite response, drifts slowly to a value. If the pole was over here, it'd be stable. It wouldn't drift. It would be under control. If the pole was over here, it would be very unstable, and not only would it drift, it would actively go mad. So by plotting your poles and your zeros from your transfer function on a little graph like this, just seeing where they are, you can instantly tell whether your system is going to behave itself or not. Okay? So poles on the left are stable, poles on the right are unstable. That's really all you need to know about them. Now, what does that really mean? So if we plotted this as a surface plot, okay, then the response is in the z direction, and this is in dBs. I've plotted it in dBs. So the amplitude response is in dBs and goes vertical. And you can see now that we've got a plane for this S. We've got this sigma and this j omega. All right? And that's the full response of the system in terms of a mountain. Okay? If we take a slice down this mountain along the sigma or the real axis equals 0, i.e. the j omega axis where the frequency is, and take that slice, we get the steady state frequency response. So the steady state frequency response is just a slice down that axis there. But there's a whole load of other stuff hiding in there. But that's okay. So the red line traces the surface where sigma equals 0, and a slice through here will give us a steady state frequency response. And you can see that the pole will give us an infinite response on the axis if it went all the way up. I just can't plot that. So what we'd like to do is move the pole somewhere else. We don't want a pole on that axis because it's unstable and we don't want that. So what can we do? All right, so we need to think about what we can do. And what we can do is we can put a resistor in parallel with the capacitor. Yeah? And a moment's thought, we've got a moment, we'll spend that moment in thought, thinking about what happens to this circuit at DC and infinity intuitively. So what happens at DC to this circuit? Just by looking at it. DC, omega equals 0, what happens to the capacitor? Any takers? Yeah? It's an open circuit. So it's not really there as far as the signal's concerned. So what are we left with? Resistor. And what kind of configuration does that make that system? It makes it into a straightforward voltage amplifier whose value is going to be R2 over R1 because that's not there for DC. So at low frequencies, this just looks like a normal amplifier with a controlled gain of R2 over R1. So that's not infinite. That's controlled. We've got control over that now. Okay. Now, what happens at high frequencies? The capacitor becomes a short circuit. Any current going around here will go, I want to go down the easy route, not the hard route. Yeah? So effectively that resistor's not there anymore because this is a very low impedance path. So we're back to what we had before, which means we get zero or very low response in terms of output at high frequencies. Yeah? Just by looking at it. You say, what happens at low frequencies? What happens at high frequencies? At low frequencies, that goes away. It looks like a normal amplifier. At high frequencies, that becomes a short circuit, so that goes away. It looks like it's got infinite, or loads of feedback anyway. And so nothing much will happen. Right. Clever stuff. Bit of basic knowledge, bit of thought, and that's what we've got. We can then start to plot that by doing exactly the same analysis. Virtual ground analysis. We say, what's the value of the impedance in the feedback loop? What's the value of the impedance in the input side of it? Divide one by the other. Okay? So capacitor in parallel with a resistor is equal to Z1, Z2 over Z1 plus Z2. So we just put the numbers in. Looks a bit complicated, but it boils down to that. And then we can do, that's just Z2. So we can do Z2 over Z1. Z1 is R1. Becomes 1 over 1 plus SCR2. Okay. Whereas before, certainly in that bit, we only had that. Now we've got a 1 in it, which means the pole of this is not when omega equals 0. We solved that whole lot now. It's not equal to 0, it's equal to 1. So that tells us it no longer has an infinite response, which is good. We expected that from looking at the diagram anyway. Okay? And that's just telling us what we already know. Sort of obvious as C is open, circuit at DC. So that tells us what's going on there. So what we'd like to be able to do is maybe plot that. And we've run out of time. So we will plot that and finish this whole lot off next time, which I think is it's going to be Monday, isn't it? Yeah, because Bob was doing some changes. He sent an email out. I can't remember what he said. Anyway, next time with me, whenever that is, we'll finish it off and we'll show you how really useful this can be when it starts to get a little bit more complicated. And it makes life so much easier for drawing these responses.
Is it okay if I check one of my answers to one of the questions of the past paper with you to see if I did the W circuit correct?
Not now.
Nah?
No, not now, because we've got to leave. And that could take a long time. I would scan it.
I just want to ask.
Scan it and email it to me.
The capacitors go away, right?
At the signal frequencies,
Okay.
not at DC. If you're doing a DC response, to calculate collector current, capacitors are open circuit.
Okay. I might ask you again next time. Is that okay?
Yeah.
One more time.
Why is there a negative sign there?
Because the response is this type of configuration. The gain is minus Z2 over Z1 because of the phase inversion.
Yeah.
So a minus 1 will fall out of the equation.
For this part, it will fall out. So
That's magnitude.
yeah.
So there's no minus signs in magnitudes. But if you haven't got a magnitude, then the minus sign is there. And it just tells you about the phase. So I was saying, a phase is hidden in these equations if you're not careful.
Right.
That's a phase shift of 180 degrees. It's an
Okay.
inversion. You know, if you've got a signal that rises into the amplifier, you'll get a signal that's falling, coming out of the amplifier, just bigger. It's opposite.
Yeah. Okay, thank you.
Yeah, no, I'm not going through exam questions today. I can't do that. No, I'm not going through exam questions today.
I just had a quick question about the Bode plot.
Yeah.
You mentioned when it is at different points across the x-axis, but what if it doesn't? Its x value is 0. But that's the steady state.
That's DC, yeah. Yeah.
Okay.
So some people, it depends what you're plotting. Some people will do a log-log plot, and then you don't officially have a 0, but you get so close to 0 that it doesn't make any difference.
Okay.
Some people will plot a log plot and a linear plot, which allows you to go to 0 and make some kind of approximations on the way.
Okay.
The thing is, if you're going to plot a proper blow plot with a log-log response, you go as close to 0 as is sensible that you need. Because a lot of time common sense applies when you say, I know what the response is at DC, so I don't need to plot all that way, because that's just causing me a great deal of trouble in terms of plotting it. So I won't bother. I'll accept that I know it's going to be, because quite often you'll go down to 100 millihertz, 10 millihertz, 1 millihertz. I mean, how close is a millihertz to 0? You can keep going in orders and powers of magnitude if you really want to, but all you end up with is usually a flat response. And you just say, okay, well, it's obviously nothing horrible is going to happen in the remaining 0.0001 of a hertz. And you'll know from the equation anyway what you expect.
So on the Argon diagram, it can't just be on the y-axis. It has to have.
Well, X and Y, the Argand diagram is plotting the Z function,
Yeah.
the S number, and the Z direction is showing you the magnitude response.
Okay.
Yeah. So the magnitude of 0 is up here somewhere because it's a three-dimensional plot. It's a surface plot.
Okay. I think so.
Yeah. So if you plot the X, because plot the XY, that's fine. But the third element, which is what you want, is the magnitude. You just put in the third dimension.
It's a straight line up.
Yeah, it's like a mountain. So at 0, for that particular one, the mountain would have an infinitely high peak at 0. And then if you take the slice through the 0 axis, you go right up the slope of that mountain to infinity. So what we'd like to do is move that mountain somewhere else on the diagram, then take the slice through the 0 axis, and you'll find you won't go up, you'll just go over the hill and come down to the side. And we'll get a picture of that next time. So.
Okay. Thank you.
So the omega in J omega
Yeah.
is essentially the same as the P, or it's part of the P operator, or
Yeah. P equals J omega.
yeah, P equals J omega,
Yeah.
including the J, not just the omega
Yeah.
part.
Well, the J is only important if you're looking at the S number, really.
Well, yeah, so yeah, but essentially P is omega. P equals omega. Yeah.
Well, J omega, yes, but omega, yes.
J, okay, J omega.
Yeah, I'm not doing exam questions today.
I just wanted to ask,
Yeah, I know you just want to, but
not about specific about this one, but about like when you tell us an op amp is ideal, we can use